get going. That looks good. That looks good. Okay. Yeah, sorry about the orange. But we found a good marker. Okay. So, we're starting on the next section today. The next section is on closed sets. So before we get into closed sets, let's remind ourselves what an open set is. What's an open set? A what? Yeah, it's just a member of the topology. If it's in the topology, it's open. If it's not in the topology, it's not open. Now, closed is not the opposite of open. We're not talking about doors. We're talking about sets. A set can be open. A set can be closed. A set can be open and closed. A set can be neither. So it's just a property that it has. And it's just a name that we call one open, and it's just a name that we call one closed. So don't read too much into the name. They are closely related, though, and we'll see exactly how. So an open set is a member of a topology. Let's remind ourselves of exactly what topology is. Topology has three properties. First property is what? The empty set is open, and the entire set, the entire space that we're in, X, is open. So the entire set has to be in there, the empty set has to be in there. Number two, what does number two say? The intersections of what? Is that an arbitrary selection, or is that n of them? A finite. Select a finite number of open sets in tau, intersect them all together. That thing better also be in tau. So any finite intersection of open sets is open. And then the third one, that's the easy one. Any arbitrary collection of open sets, its union is open. The union of an arbitrary collection of open sets is open. Maybe finite, maybe infinite. Maybe you pick one thing, maybe you pick everything. So those are the three properties that the open set satisfy. Open sets satisfy these three properties. We're going to see closed sets satisfy almost those exact same three properties. It's going to be a slight tweak on these. It's like we're going to swap those two. Before we get to that, let's get to closed sets. Before we get to closed sets, we now need to talk about set complement. Have we already talked about set complement? Set complement. Just remind you what it is. So let U be some subset of X. So the universe we're in is X, and U is just some subset of X. So X is our universe. Then A, which is equal to X minus U, is called the complement of U. Tell me in words what A is. Everything that U isn't. It's everything that's not in U. If something's in U, it's not in A. And if something's in A, then it's not in U. So we can think about A as being the set of all points not in U. And that's how we're going to think about the complement from here on out. And it's going to be understood that the universe we're talking about is X. It's all the points in X that aren't in U. We're going to stop saying it's all the points in X that aren't in U, and we're just going to say it's all the points that aren't in U. And it's understood from context what we mean. So from here on out, we will denote the complement of a set with that superscript, if you want to say subscript, that superscript of C. If we put a superscript of C up there, that means a complement. So if A is equal to X minus U, then A is equal to the complement of U. And that's how we're going to start marking the complement. You may have seen from earlier classes before where we mark the complement of some set with a line above it like that. That's common notation. This is going to be special notation that we talk about next week, maybe this week. So we reserve that for something else. So in this class, we're going to use the superscript of C to denote a complement. All right? So now we're ready for the definition of a closed set. Let X tau be a topological space, then some subset of X is closed in X. So A is a closed set if and only if a complement is open. So if the complement of A is in the topology, then A is closed. What does it mean for a set to be closed? It means its complement is open. That's it. That's all it means. Okay. Let's dive into some examples. So, hey. Oh, Peter might have been one of the original students. Were you at the first night class we did? I think logic out of my house. Yep. Okay, he was. All right. So now we're going to go look R sub st. That's our notation for the standard topology on R. Let's remind ourselves. So first off, what's R? When we think about R, we think about the real number line, right? Okay. What's the standard topology on R? The empty set is for sure in the standard topology, and the entire set R is for sure in the topology. That's always the case for any topology, right? What else is in there? No. The power set of R would be the discrete topology on R. That would mean everything is an open set. The standard topology on R. It is all the open intervals we can make, A comma B, and any union of open intervals. It's a definition. So we had a basis. We said we proved that beta equal to the set of all open intervals A, B, where A is less than B, and obviously they're both real numbers. We proved that this is a basis, and it generates a topology. And the topology it generates on R, we define to be the standard topology. So any union of open intervals, any open interval and any union of open intervals is what we mean by an open set in the standard topology. So, question. If I take all the points from here, not including that point, to here, not including that point, so I take all these points, is that an open set in R? Yeah, that's an open interval. What if I also include all the points from here over to here? So I have all these points and all these points. Yes, that's another open set. Write that set out. That's another set in tau. How many open sets are there in the standard topology on R? An infinite number. Let's look at just this open set. How many elements are in this set? An infinite. Are there any open sets in R? Talk about the standard topology on R. Are there any open sets that don't have infinite elements? No, because there are always going to be open intervals or unions of open intervals. Which one got you? Obviously the empty set is open. But outside the empty set, every other open set has infinite elements in it. All right. Remind you of the standard topology on R. It's one that we're going to come back to over and over and over again. It's a topology that you use when you develop calculus. It's one that we're very interested in. You can think about calculus is just an analysis of the standard topology on R. That's what it is. Okay, so that's a standard topology on R, reminding ourselves of it. Let me ask you some other questions. Question, is the set containing the points 2, 4, and 7 open in the standard topology on R? Just those points. So we're going over here. Here's 0, 1, 2, 3, 4, 5, 6, 7. We're saying this point together with this point together with this point. Is that an open set? No. Why not? How can I get 4? I'm only allowed to use open intervals. Any little open interval I create to try and get 4 is going to include infinitely many points to the left of 4 and infinitely many points to the right of 4. I can't use an open interval and just get 4. So if I told you with an open interval, try and create this set now. You have to use open intervals, try and create this set. There's no way to do it. One sanity check is, how many things are in this set? 3, a finite number. Every open set in R has infinite elements in it, because it's always open intervals, with the exception of the empty set, obviously. Outside the empty set, every other open set in R has infinite elements in it. So any set I can just enumerate the elements of is definitely not an open set in R. Let's try another one. What about all the points from 2 to 5, not including 5? Trying this out. Talk about this. Here it is pictorially. 2 to 5, not including 5. Is this an open set? It has infinite elements in it. Yeah, there's no way to get 2 using open intervals. Any open interval I use to try and capture 2 is also going to capture a little bit of space just to the left of 2. And in that little bit of space, I don't care how tiny it is, you caught infinitely many real numbers. Doesn't matter how much you zoom in, just take a little snippet of it. You got infinitely many. Sorry. So no, this would not be open in the standard topology on R. Okay, so that's reminding us of the standard topology on R. Now we're looking at closed sets. So standard topology on R, should stop erasing this, standard topology on R. My first question is, well, it doesn't matter what 0 is. Here's A, here's B. They're just 2 real numbers. Is the closed interval AB, is this, all those points, is this a closed set in the standard topology on R? Yes. Is that closed? How do we determine if a set is closed? If its complement is open. So here's a closed set. Let's draw underneath this line, let's draw its complement. What's the complement of this set? It's everything from negative infinity to A, not including A, union together with everything from B to positive infinity, not including B. Open interval, union of open intervals, that's sure open. And so this closed interval is in fact a closed set on the standard topology. And that's why we call these things closed. It's where the name ultimately comes from. So closed intervals are closed on the standard topology on R. Open intervals are open on the standard topology on R. Isn't that convenient? One of the times mathematicians got the names right. Okay. Let's look at another example. Let's look at the set just containing 2. Is that closed? Is it closed? You don't say why not, you ask why. What's the complement of that set? It's everything but 2. Let's write that out. That's everything from negative infinity to 2, not including 2. Union together with everything from 2 to infinity. Is this open? Yeah, so that's closed. That's the only check. Is its complement open? Then it's closed. All right, let's check this one. Is the empty set closed? I didn't ask if it was open, I asked if it's closed. Is everything closed? No, everything is not closed. Is the empty set closed? I don't know. Let's think. What is the complement of the empty set? R. Is R open? Okay, then the empty set's closed. So it's open and closed. So we call it clopen. No. Let's now look at R. Is R closed? What's its complement? Is its complement open? So it's closed. So always and forever, in every topology, the empty set is both open and closed, and the entire set itself is both open and closed. And there may or may not be other sets which are both open and closed. There could be some other overlaps, there could be not some other overlaps. All right, so he asked a very natural question. This is done. Is everything closed? Well, let's see. What if we would have done all the numbers from 0 to 1 in a union together with all the numbers from 2 to 3? We're including 0, 1. We're not including 2 and 3. Is it closed? Let's look at its complement. I think you guys are just guessing based off of intuition rather than thinking through the complement. Let's think through the complement. Okay, so we're going to include everything from negative infinity to 0, not including 0, union together with everything from 1, not including 1, to 2, yes, including 2, union together with yes, including 3, to infinity. 3, sorry. To infinity. Is that an open set? No, this isn't open. There's no way to get an interval containing just that 2. You can't have that terminating point. Remember, any open interval that's going to get 2 has to get something a little bit to the right of 2 as well. Same problem with the 3 there. So question, is this top set closed? No, so it must be open. No! It's not open, it's not closed. It's just a set. And most sets are just sets, and that's all they are. We just happen to pick ones that are special and work with ones that are special and have these interesting properties. And so it's natural for us to work with those ones. But if we had some random generate a set for me button that truly just generate a random subset of R, the majority of the time the set would be neither open nor closed. Just be some subset of R. So it's only special sets that have these properties. Very special when you have an open set. It's very special when you have a closed set in the standard topology on R. Okay, I think we're getting some intuition for these things. Next one. The integers. So we're still on the standard topology on R. The set we're considering now is the integers. Is that open or closed?
That is
closed. Is it? All the integers? Or is it neither? Think carefully through it. So here's 0. Yeah, it's neither, right? So we're talking about this point, this point, this point, this point, this point, this point. Tell me when you're sick of hearing this point.
What? Oh, I'm drawing an integer.
Okay, there's the integers. Is this set closed? No. Wait a second. What's the complement? Let's stop just guessing and let's actually think this through. This is taking, let's write it. So it's all the numbers in between. So for this gap right here, we're taking the numbers from 0 to 1, unioning that together with all the numbers from 1 to 2, unioning that together with all the numbers from 2 to 3, unioning ... going on forever, and unioning backwards. -1 to 0, unioning ... on forever. That's the complement of this, right? It's all the spaces in between. Is that an open interval? What about that? What about that? So we're just unioning up a bunch of open intervals. So it's an open set. So the integers are closed.
What? Are they open?
No, they're closed. The integers are closed. We are saying this is closed. All right. I might have accidentally said open. Sorry. The complement of Z, so here's Z. Its complement is up here.
Okay.
Right? This is Z. Just those points. This is Z complement. All the space in between each of the points. Never including the actual integers. Just all the numbers between the integers. So the integers are closed. What about the rationals? The integers are closed. The rationals have got to be closed, right? I wouldn't have said that unless I was trying to trick you, right? The complement is the irrational numbers, yes.
Would that be open interval? You write that?
Is the complement of the rationals open? First off, let's check. Are the rationals open?
Yeah.
Are the rationals an open set on R? Let's start with that. You guys know what rationals are? All the fractions? Okay. So if we were to plot all the rationals then we'd have to get, 0, this fraction, this fraction, this fraction, da, 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 da. And if we plot it all, we're going to fill in this whole number line plotting every point. But there's numbers that we're skipping, too. Between any two rationals, there's an infinite, well, shouldn't say that. Between any two rationals, there's an irrational. There's an irrational between any two rationals. Any open interval I create on the number line is going to contain an infinite number of irrationals. So I cannot construct the rationals with a bunch of open intervals. Because even one open interval already has irrationals. No way around it. So I can't have an open interval that contains no irrational numbers. So it's not open. Is it closed? Or in other words, are the irrational numbers open? And the answer is no. There's no open interval I can create that only contains irrationals. It's always going to have some rationals, and it's always going to have some irrationals. So the rationals are not open, and the rationals are not closed. The integers are closed. The naturals are... The naturals are also closed.
0 is closed. Infinity is open.
Here's the complement of the naturals. Union together with all the numbers from 0 to negative infinity. All the negatives, union together with the numbers between 0 and 1, union together with the numbers between 1 and 2, union together with the numbers between 2 and 3. No, this is now the complement of the naturals. So get rid of that, get rid of that. So just redraw that. So the naturals are just 0, 1, 2, 3, 4, 5. So this, we're missing 0, we're missing 1, we're missing 2, we're missing 3, we're missing 4, we're missing 5.
Why are you using negative infinity? Naturals.
Because it's the complement.
We're looking at the complement of the naturals in R. Here are all the real numbers that are not naturals. Yes, we're in R. So all this, we're talking about the standard topology, so our big X is R. Standard topology on R is the example we're talking about. So here's big X in our universe. Okay, so we're all clear now? Okay, so let's see, we did the naturals, we did the integers. Let's see, naturals were closed. Rationals, neither. Integers were closed. All real numbers, was that closed? Oh, no, that one was open.
That's closed.
Oh, it's open. It's both. And what about the empty set? That's also open. Good. Okay, getting comfortable with the standard topology on R. Long time for one example. Next, we need to talk about closed balls. Before we talk about closed balls, let's first remind you about what an open ball is. Pictorially, an open ball is, I take some point X with some radius R. An open ball is all the points whose distance from X is less than R. So it's all these points, not including the boundary. Those are all the points whose distance from X is less than R. If it was on the boundary, its distance from X would be exactly R. And if it was outside the boundary, its distance from X would be greater than R. So this is called an open ball. So we used B with X comma R to represent this. The set of all points whose distance from X is less than R. Writing it out using set builder notation, we said B of X comma R is equal to the set of all Y in R2, all the points in R2, such that the distance from X to Y is less than R. That was the definition of an open ball. A closed ball, we represent a closed ball by putting a line above it like that to remind us it's closed. And a closed ball, exact same definition, except for less than or equal to R. And so the only difference between an open ball and a closed ball is we include the boundary. Huh?
Why is that important? So,
Well, an open ball is going to be an open set, And a closed ball is going to be a closed set.
Yeah.
And it's going to turn out that you can union up open balls to get open sets. And I think you can union up closed balls to get closed sets. You can definitely intersect them. You can union up a finite number, for sure. An infinite number, I'd have to think about it. Can't see why not. But I'm not positive, so I don't dare say it. It appeals to my intuition that yes. Anyways, so that's a closed ball. So let x be any point in R2 and let R be any positive real number. Then the closed ball, notice there's that line above it, the closed ball centered at x with radius R is equal to all the points y in R2 such that the distance from x to y is less than or equal to R. And we call it a closed ball. Okay. Now I'm going to prove to you that a closed ball is actually closed. So remember, closed ball is just a name. I need to prove that this is actually a closed set. Now before I do that, let's just look at some examples of sets now on R2. So spend a lot of time trying to reestablish your intuition for R1 and the standard topology on R1. Let's now look at the standard topology on R2 for a second and try and reestablish some intuition. Now tell me in words, what's the standard topology on, first off, what is R2? What do I mean by R2?
It's
Table.
real numbers intersect with
It's real numbers crossed with real numbers. What would you tell a first grader it is? It's a plane. It's the plane, the XY graph, the plane. That's what we mean by R2, the plane. The real number crossed with the real numbers. It's why you use two numbers to represent a point in the plane. It's R cross R. Okay, so here's a bunch of sets in R cross R. You with me? This is this line segment intersecting this line segment. This is we include all the points in this kind of border here and then that point in the center. This is including all the points in this arch. This is all the points out here, including these boundary points, not including those boundary points. And then this is just an open square. Okay. I want you to, based off of your intuition, tell me which of these are open, which ones are closed, which ones are both, which ones are neither. So we're starting with this. Open, closed, what do we think? Definitely not open, right? Remember, how do we get open sets in R2? Anything we can represent with unions of open balls. So the standard topology on just R, we're using unions of open intervals, which are one-dimensional balls. In R2, the standard topology on R2 is anything we can create with unions of open balls, two-dimensional balls, which we call circles. And three-dimensional balls for the standard topology on R3, and R4 and R5, and going up and however far you want. So, question. Is this closed? Let's think about its complement. What is the complement of this? That's all the points in the xy plane that aren't these points. So we don't have those points, and we don't have those points. Is that an open set? Is this open? Yeah. So this is closed. All right. Next one. Let's draw out the complement of this thing. So that would be we're missing that point. We have all these points. And then we have all the points out here. So we cut out that piece and then we puncture a hole right there. Is that open? Yes. So that is closed. Next, is this closed? Yes, because its complement is open. Is this closed? Let's think about that one. Let's draw its complement. So everything that's not included, let's see, we have this middle disk here, including the border. So we got the middle disk, and then we're missing those lines, but then we have everything out here. Is this an open set? It's not an open set. How do I know it's not an open set? There's no way for us to get that border. Any open ball I construct that contains one of these border points has to go a little bit outside of that as well. I can't get an open ball to contain that border point without the open ball coming out here a little bit. There's no way to do that. It's the same problem we had with the intervals on R1. You know that in R1, going from 1 to 2 like this is not open. Why? Because there's no way to get 1. Because any open interval you place around 1 gets a little bit this way. Same problem here. You can never have boundary points in R2 because if you have one of those boundary points, there's no open ball I can create that contains that boundary point that doesn't also contain a little bit beyond the boundary. So it's the same problem, just two-dimensional version of the problem rather than one-dimensional. So this is not open and this is not closed. Let's look at this one. Is it open? Yeah, what about its complement? Its complement is also open? Let's see. So drawing it out, we include the boundary and then everything out here. Is that open? No, because any open ball you contain, trying to get that boundary point is going to contain a little bit inside here. We're going to accidentally get bad points. So this is open, not closed. So closed, 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 open, neither. Make sense? Getting some intuition for this stuff? Okay. So let's go to our first proof of the day. So I'm proving this. Closed balls are closed on the standard topology on R2. So let's prove it. 1. Let B X R be any closed ball in R2. Okay, so we got some closed ball. We're trying to prove that this is in fact a closed set. What does it mean for a set to be closed? Its complement is open. So 2. Let U equal BXRs, the closed balls. Move the any, make it a little bit short so we can parse it here. Let U be the complement of that closed ball. Let's draw a picture really quick and try and give you my proof strategy here. So here's what I'm thinking. So here's our closed ball, XR, like that, right? So here's our ball. So I'm going to draw U over here to help us see both at the same time. U is a complement of this, so U is going to, the closed ball, obviously we're including all the points inside. Okay. U going to be all the points out here. So this is U, this is our ball. U is the complement of our ball. I'm trying to prove that U is open. How am I going to prove that U is open? Unfortunately, that is not sufficient. We have to prove it.
Any union of open balls.
Here's how I'm going to do it. I'm going to show that for any point in U you choose, call it little y. For any point y in U you choose, I can find an open ball containing y. I can construct an open ball containing y such that that open ball doesn't intersect this open ball. Or in other words, that open ball is a subset of U. And so I'm going to call that open ball B sub y. I'm going to show that for any y in U you choose, I can find an open ball containing that point where that open ball is a subset of U. So I'm just going to show that for all y in U, comma, there exists some open ball B sub y such that y is in B sub y is a subset of U. Then U is going to be equal to the union. U is going to be the union of all those balls. For every U, for every y in U, y in U, union up its open ball, and that's going to give you back U. because we have one of these open balls for every single point y in u. And so we just express u as a union of open balls. That's what it means to be open in the standard topology on R2. You are a union of open balls. That's how we prove it. So that's big picture how this proof is going to work. Let me show that for any point in u you choose. I can find some open set containing that point. And then u is just a union of all those open sets. So u is open. The open set is going to be one of these open balls. Is it clear? Big picture what I'm going to try and do? Okay. So, let u equal the complement, comma, and let y be any arbitrary point in u. Pick any point y in u, I don't care what it is. 3. Let epsilon is going to be the radius of this ball. So here's my x, here's my r, here's my epsilon. I want my epsilon, how small do I need to make sure my epsilon is? I don't want my epsilon to be too big, right? I need to make sure, so first off, epsilon has to be a positive number, so epsilon has to be greater than 0. But I also want it to be small enough that doesn't actually go into this ball. So how small do I have to make it? What does it have to be less than? Not necessarily r, because we can make it the distance from x to y minus r. So we want it to be less than this distance. So here's the distance from x to y. Here's r. So take the distance from x to y minus r. That gives us this distance. As long as epsilon is less than that distance, we're good. So let epsilon be less than the distance from x to y minus r. Now I should probably think about this for a second, make sure we're not cheating. How do I know that the distance from x to y minus r is in fact a positive number? How do I know that the distance from x to y is actually bigger than r? Right? This is positive if this number is bigger.
Because y can't be in the radius, it can't be in the circle that r is.
Right. If the distance from x to y was equal to r, then y would have been in the closed ball. But we know y is not in the closed ball because it's in u, which is the complement of that. So it can't be equal to r, and it can't be less than r, otherwise y would have been in here. And we know y is not in there. So I know that this is a positive number. So when someone picks a point, they pick a y, first thing you do is you say, okay, so calculate that distance and then just pick some random number. Say that this came out to 0.1. Our epsilon then could be 0.05. Our epsilon just needs to be some number smaller than this difference. Doesn't matter which one. Right? So once someone picks a y, you can now calculate that distance. You know the r, you know that distance. You can find an epsilon that's small enough. So that's the logic there. So let epsilon be any number between 0 and this number. Doesn't matter which one you choose. Any of them will work. And it remains to show, that the ball centered at y with radius epsilon is a subset of u. That's what we need to show. We need to show that this ball is actually a subset of u. Because if this ball is a subset of u, and I can find one of those balls for every point y in u, then u is just a union of all those balls. So if I can show that this ball is a subset of u, then we're done. Because I just barely showed you how to, for any point y in u, find an open ball containing y that's a subset of u. And so then u is just a union of all those open balls. And so u is open. Remember, we're showing u is open. That's big picture what we're doing. How do we show u is open? We show it's a union of open balls. Okay, so that's where we're going to go from here. So I just need to show that this ball is a subset of u. Or in other words, the intersection with this ball and this ball is empty. U, comma, or in other words, I need to show that the ball centered at y with radius epsilon intersected with the ball centered at x with radius r is equal to the empty set. Same thing. If I can show that there's no intersection between those, then this ball must be entirely in U. Because this is everything, because U is everything that's not in this. And so if this has nothing in common with this, it must be entirely in U. Okay. So that's what I'm going to prove. I'm going to prove it by way of contradiction. I'm going to assume that there is something in the intersection and show that that leads to an impossible worldview. Proof by contradiction. I'm going to show it's impossible for something to be in the intersection, therefore nothing is in the intersection. That's the logic there. So 4. This is a common proof technique, so we have a shorthand for it. So assume, you'll see this a lot, by way of contradiction, that there exists some point z such that z is in this ball and z is in the other ball. So assume by way of contradiction that some point is in both these balls, or in other words, they have some intersection. So we got some point z. Trying to draw an impossible picture. Obviously, I can't draw z in both the balls because that's impossible. But so we got some point z. We're pretending that maybe somehow it can actually be in both those balls. We're going to see how that's impossible. So assume by way of contradiction that there's a z in both of those. Okay, now we're going to get a contradiction. Let's remind ourselves of the triangle inequality. What was the triangle inequality? The triangle inequality is if I have any 3 points, x, y, and z, x, y, and z, the distance from x to y plus the distance from y to z is always less than, or is always greater than or equal to the distance from x to z. You can't take a detour and get there covering a shorter distance. The shortest path between 2 points is a straight line. So, the distance from x to z plus the distance from z to y has to be greater than or equal to the distance from x to y. So here's where I'm using the triangle inequality. Make sure it makes sense. So the distance from x to y is less than or equal to the distance from x to z plus the distance from z to y. That make sense? The distance going straight to y has to be less than or equal to the distance going to z first and then from z to y. Okay, let's play with this. The distance from x to z, so this is less than, the distance from x to z, if z is in this ball, the distance from x to z has to be less than what? R. Has to be less than or equal to r if it's in this ball. Sorry, it can be on the boundary here if it's in this ball. Okay, so it has to be less than or equal to r plus the distance from z to y. Well, this is going to turn out to be less than. Because the distance from y to z, if z is in this ball, the distance from y to z has to be less than epsilon. So if z is in the first ball, the distance from x to z has to be less than or equal to r. And if z is in this second ball, then the distance from z to y has to be less than epsilon. So the sum of these two distances has to be less than r plus epsilon. By definition, epsilon is less than what?
The distance from x and y minus r.
Epsilon is less than this value. So if I replace epsilon with this value, I could have only made my number bigger. I couldn't have made it smaller that way. Because this is more than epsilon. So I'm going to replace epsilon with this value, and we could have only made our total sum here bigger. So this is less than r plus the distance from x to y minus r. R's cancel out. That's just equal to the distance from x to y. Now notice what I got. The distance from x to y is less than the distance from x to y. Well, less than or equal to, but then less than here.
Yeah, because you
And less than here.
from there.
Oh.
Because this is tagging it on like that. So there's our contradiction. Usually you do two arrows pointing back and forth at each other like that to tell the reader, there's your contradiction. Well, not quite yet. 6. Therefore, this is true. Therefore, B, the ball centered at y with radius epsilon, intersected the ball centered at x with radius r is equal to the empty set. This ball has nothing in common with that set. And so this ball has to be completely in the complement of that set. If this ball has nothing in common with that ball, then this ball must be in the complement of that ball. Look at this ball's complement. This has to be in there. So in other words, we just barely showed that the ball centered at y with radius epsilon is a subset of U. Huh? Which we can get from the picture.
Which proves that U is open, which proves that.
Well, so far, what did I show? I showed for any point y in U you choose. I can find an open ball that's a subset of U that contains y. So then union up all those open balls, and that gives you U. So U is a union of open balls. So then U is equal to the union for all y in U of each of these open balls b sub y. We just went through the process of how you find one. Now pick another point y, repeat the process. Now pick another point y, repeat the process. We do that for every single point y in U. Take all those open balls that you get, union them all up, that gives you U. Which gives you that U is in the standard topology on R2. That's our tau. Standard topology on R2, that's our tau. That's our topology. Which gives you that, remember, U was the complement of our closed ball. So since U is open, that gives us that the ball, the closed ball at x with radius r, is closed. And that's what we were after. So proving that a set is closed, you kind of have to do it a roundabout way. You go get its complement, show that its complement is open. Any questions on that proof?
Is this similar to how you use your epsilon delta definition in tau? When you define it?
How I use my epsilon delta definition in tau?
In calculus?
In calculus. I don't know how I heard tau from that. Okay. Oh, you missed the very start. Okay. The standard topology, calculus can be thought of as the analysis of the standard topology on R. That's what calculus is.
Okay.
So shortly, next week or the week after that, we'll be talking about limits. And yes, the limits here are the exact same thing as limits in calculus. It's just that the limits in calculus are just limits on the real numbers. We're going to talk about limits for topologies. We're talking about all limits all in one go.
Do you use the same definition?
So it comes out the same. It's logically equivalent. But the definition that you use for a limit for the real numbers is a much more restrictive one because you only care about the real numbers in calculus. And I didn't do real analysis with you. I did an actual Calc 1. Calc 1, they completely hide you from a limit until they want to talk about the limit of a function at a point. And they dump it all on you in one go. And so they essentially give you the epsilon delta definition for continuity. And yes, one of the things we will show is that the definition for continuous in this is logically equivalent to the epsilon delta definition of continuity in calculus. But it turns out the general definition of a continuous function is way, 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 way easier to say than the epsilon delta definition of a continuous function in calculus. Definition, I'll give you it right now. What's a continuous function? It's a function such that the preimage of every open set is an open set. Take an open set, look at its pre-image under that function. Is it still open? Ah, that's continuous. When you run the function backwards, the image, you plug something into a function, something comes out. The thing that comes out we call the image. The thing you put in is called the pre-image. So if what comes out is an open set, go back and look, what did we plug in? Is that an open set? Yep. Okay. Continuous. We'll get to it. That's jumping ahead a bit. I think that's like chapter 4.
What chapter is this?
This is the end of 1. 1 ends with close sets. Well, that's not true. It goes into some application stuff, and I'm torn as to whether or not to go over it.
Application.
Yes, so like how we use topologies. So we use a digital topology to do things like letter recognition is a common one. Yeah, so when you're trying to recognize what letter something is, like when I say, what is that? Hate. You would not be good at it. It's a B. Now notice that it's a lot of the geometric properties aren't that important when you're trying to figure out. See, you don't even know homeomorphisms yet, which is why there's almost no point talking about this. But so in letter recognition, you care a lot more about just the topological structure of the thing to determine what letter it is, like how many loops it has. How many loops something has, that's a topological property. And so number of loops is one of the things you definitely care about in trying to recognize a letter. Another place that we use topology that it's bringing up is in determining how close one genetic piece of information is to another. So take some string of nucleotides, and you're trying to determine how close are these things to each other.
Like distance-wise, or
Well, we just use it some way of talking about how close they are. So I have some string of nucleotides. So like on DNA, you see like G, A, C, T, A, whatever. And you see just strings of nucleotides. You've seen that for like genetic code. So you have one genetic code, you have another genetic code, and you want to know how close are these things to each other. How similar are they?
There we go.
How similar? Sure. And so we might have G, A, C, C, T, A. And you think, oh, that's really close to that one because it only swaps out one letter.
but doesn't that one letter?
And then I could have some other one, which is G, C, A, C, T, A. You might think that's also the same close because it only swaps out one letter. But when you look at the actual physical structure of these things, how they actually physically lay out, swapping out one letter might completely change the way it arranges itself, while swapping out another letter might not. So it's not enough to just do some simple-minded, oh, let's just compare the letters and say how close it is. It gets a lot more complex than that. And so you actually have to look at the topology of how that molecule physically looks in space. And so that's one of the examples that he gives at the end of chapter 1. But to do that, it'd be a huge detour. And at the same time, you guys have almost nothing yet to talk about. And so it's kind of like, trust me, they use it for this stuff, and it's cool. Okay. That's why I'm torn with the application stuff. Because it is cool, but it's kind of like you just taking mine or the author's word for it most of the time. Because I can't really show you anything. Because you don't really... One chapter into a topology book. You're not ready to do the topology on genetic information. Anyways, so I'll probably skip the first couple application chapters and then try to get them later when we're further along. You can actually do more than just talk about it. I don't know. Anyways, lost where I was. We proved this. We did that. We're getting some experience, doing some examples. All right. I think I was going to ask you to find the close sets. That's what I was doing. Okay, close sets. So now we've got some set X. What set is it? I don't know. But its topology is the power set of X. So which sets are closed? The empty set's closed. Okay, we got one. The empty set's closed. The whole set X is closed. Let's think of a concrete example. Let's say for a second that X was equal to the set A, B, C, D. And what's this topology? It's the power set of X. So every possible subset. Okay. Which sets are closed? So we got the empty set, we got X. Are you guys getting confused by?
Nothing in between A and B.
There's nothing in between it. Here's our topology. So our topology is, let's start writing out our topology, because you might be getting confused by that. It's a set of all possible subsets. So we have the empty sets in there. The set containing A, the set containing B, the set containing C, the set containing D, dot, 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 all the way to the set containing A, B, C, D. These are all the open sets.
Why are they not all closed?
These are all the open sets. I just explicitly wrote out the topology. Now I'm asking for what are the closed sets? Someone told me the empty set. Yes, the empty set is closed. Why? Because the entire set X is open. Then they said X is closed. How do I know X is closed? Because the empty set's open.
What's the complement of A? Everything that's not A, B, C, D. Are they all closed?
They're all open. They're all closed, and they're all open. Because we're saying, this says everything's open. And if everything's open, then everything's closed. Take an open set, take its complement. You still have something, and everything's open. So the complement is also open. Every set's open, and every set's complement, which is also a set, is open. Right? Okay, so there's an example of a pretty useless topology. A topology where everything's open and closed. We don't like that. All right. Now let's do this concrete example. So once again, X is A, B, C, D. And here's our topology. First question, did I cheat? Is this actually a topology? What do we need to check? First off, is the empty set in there? Yay! Is the entire set X in there? Yay! Okay, is any finite intersection in there? So pick a finite number of them. We only have a finite set, so we can say, is the intersection of any of those things still in there?
Yeah.
And then is the union of any of those things still in there? Who can see the one we're missing?
We're missing the intersection of A, B, and C. Or C.
Nope, we have.
A, B, and C, D intersected together is right there.
Oh, intersection.
Oh, did you mean union?
Yeah, I meant.
Union them, and it's right there.
Oh.
The intersection of A, B, and
A,
B,
B, B,
C,
C,
D.
D, yeah. That's X.
No, because that should be the second.
The intersection of what?
A, B, and B, C, D.
Its intersection is the set containing B.
Oh, no.
The intersection of this and this
Are you saying there is one?
is just the set containing B.
Are you saying there is one?
I did say that. I lied, but kept you thinking.
Okay, all right.
Okay.
So that's
Yes.
topology.
It is in fact a topology. All right. So now, what are the closed sets? Let's write out the closed sets. Tell me what to write.
Oh,
The empty set is closed? Yep.
A, C, D.
The entire set X, okay. What did you say?
A, C, D.
He said A, C, D. Yes.
Containing A.
The set containing A? Just A? This is closed? Yeah, because that's open.
Yeah.
Complement's open, so it's closed. All right, what else?
C, D.
The second containing BC?
AB.
What did you say?
Second AB.
No, it's right there.
A and B?
AB.
Maybe it's open.
No, that one's open.
It's open, yeah.
Can't be closed because it's open.
But complement is close.
Wait, what's the complement of AB?
It's CD.
CD.
So it's close.
Oh, so it is closed.
Oh, it's
All right, so here's one that's both.
okay, fair enough.
Yeah,
And is it CD as well?
is a CD as well. Yes. So if one set's clopin, its complement is clopin.
And it has that. Oh, yeah.
Did we get them all?
Looks like it.
There should be the same many. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yay.
Is that just that one?
Yes, for every open set, there's one and only one complement. So yes, there's always the same count of open sets and closed sets. Okay. De Morgan's. Sorry for those of you who have had logic already. For those of you who haven't, how many of you have at least seen a truth table? Okay, that answers that. A truth table. Okay. Oh my goodness. You probably don't even know and or not.
At the start. How did you talk to you?
Okay. There's no way we're going to be able to hide this logical notation from you. So time to just take the bull by the horns and deal with it as it comes. So I've got two statements, alpha and beta. These just represent statements. These represent things that are either true or false. Those of you who program, these are booleans. All right. We have two booleans, two propositions, two statements, whatever you want to call it, two things that are true or false. Now there's four possible combinations for the values that these things can take on. We can have alpha's true and beta's true. We can have alpha's true and beta's false. We can have alpha's false and beta's true. We can have alpha's false and beta's false. Make sense? Okay. Now, alpha and beta, that little thing poking up, it's just two lines like that, like the top of a triangle without its bottom piece, stands for and. Very common notation. Like an ampersand. Okay. So, if alpha is true and beta is true, then alpha and beta is true. If alpha is true and beta is false, alpha and beta is false. Let me give you a concrete example. I tell you, I'm holding a black marker and I'm 200 feet tall. Is that statement true? No. I gave you an alpha that was true, I'm holding a black marker, and a beta that was false. I'm 100 feet tall, or whatever I said. So the whole statement together was false. The only way that you can say alpha and beta and be telling the truth is if both alpha was true and beta was true. Right? All right, next example. If alpha is false and beta is true, alpha and beta is false. And if alpha is false and beta is false, then alpha and beta is false. If I tell you a lie and another lie, I just lied to you twice. I didn't tell you the truth somehow. Two lies don't make a truth. All right. Okay. So that is and. Now we got to do or. Uh-oh. Alpha or beta. Or, same symbol, just flipped up now. Okay. If alpha is true and beta is true, then alpha or beta is, in this case, it's going to be true. And unfortunately, we have a problem in the English language. We have what we call the inclusive or and the exclusive or. If you are at a restaurant and you order a meal and the waiter says, okay, that comes with a side of, fries or salad, and you say, okay, both sounds good. Say, no, it's one or the other. You don't get both. That's what they mean. On the other hand, if I say to take this class, you have to take calculus or physics, and you say, I took both. Sorry, I can't do it. No, you're still okay. So we mean it in that latter sense, inclusively. All right. So in this case, true or true is true. True or false is true. False or true is false or false is false. Good. I tell you, I'm the King of England, or I'm George Bush. Is that true? No. False or false is false. All right. So there's and, there's or. Now not. Huh? I'm just trying to do De Morgan's, which is not alpha and beta is the same thing as not alpha or not beta. That's De Morgan's. That's all we need.
When are you going to introduce some implications?
When we're forced to. Or maybe they'll just go back and watch the logic lecture and be good.
Oh, yes, like one for every class you have.
Yeah, you could almost just pick one of my playlists and watch the first lecture and it will be on logic. Except for this one, because this one, we just finished the logic class right before. That one, we did a whole course on logic, but every other lecture, I usually start with a crash course on logic. So like my discrete math course, you go watch that. First one's on logic. Geometry, first class, logic.
Didn't you say you started this right? Logic?
No, logic was a class we did right before topology. We actually did a full course on logic, not just a crash course for one class. So that's why we skipped the crash course class.
So have you done topology class?
Once before.
So is there a logic on that?
Yes. So if you go look at my earlier topology from 2020 and watch the first lecture on that, it will be one on logic. It's almost how I start every single one of my classes. Logic, because you need logic. Okay. Now, negation. Not just undoes. So we really quick need not alpha, and we need not beta. And that's the not symbol, a lot like a negative symbol. That one's the most intuitive of the symbols. Okay. So if alpha is true, not alpha is false. Not true is false. Not false is not false is. So if this is alpha, this is not alpha. Tell me not beta. Good. Okay. Now, put a double line there, we got what we need. Now we're going to write not alpha and beta. And we're going to compare that with not alpha or not beta. We're going to compare these two things, and we're going to see how they say the exact same thing. And then I'll try to sententially walk you through it. So let's look at this. So alpha and beta we have right here. So this is not alpha and beta. So we're just nodding this. So what is it? Okay, and this one is not alpha or not beta. So we're just oring these two together. So false or false is, false or true is, false or false is, false. False or true is, true or false is, true or true is, true. Okay, notice that they are identical. No matter what alpha and beta are, these two things always spit out the exact same thing. Doesn't matter what statement you pick for alpha and beta. If this one comes out false, this one comes out false. If this one comes out true, this one comes out true. For any statement you choose. It's always the case. Because no matter what statement you choose, either you chose two that were true, the first one was true and the second was false, or the first one was false and the second one was true, or they were both false. For any statement you choose. Pick any two statements you want. It has to be one of those four combinations. No matter which statement you choose, these two always spit out the same thing. Now let's give you sentential intuition for this. If I say that it's not the case that I'm the teacher and 10 feet tall, right? I'm not a 10-foot tall teacher. It is not the case that I'm a teacher and 10 feet tall. What does that mean? It means either I'm not the teacher or I'm not 10 feet tall. If I'm not both alpha and beta, then either I'm not alpha or I'm not beta.
Oh.
Or you can ask, what does it mean for them to be lying? If someone tells you alpha and beta and you say you're lying, you're saying either alpha's false or beta's false. Make sense? Okay, so that's the intuition for how these two say the exact same thing. The way we say that in logic is when you distribute a not over an and, it converts it to an or. And similarly, if we did not alpha or beta, and we compare that with not alpha and not beta, they also give the same thing. So let's look at this really quick. This is not alpha or beta. So we're negating alpha or beta here. So what am I writing? Good. Over here, we are anding together not alpha and not beta. We're anding these two together. False and false is? False and true is? True or false? True and false is? And true is? And look at that, they're the same. Okay, so that is called De Morgan's. De Morgan's tells us how to distribute nots over ands and ors. If you distribute a not over an and, it converts it to an or. If you distribute a not over an or, it converts it to an and. That's De Morgan's. Okay. Because he was the first one to show this principle. He showed it with sets before it was just written out with logic, but it's just named after the guy who first discovered it, and it just sticks around. Okay, so that was De Morgan's. Now we're going to look at De Morgan's with sets. You're going to notice it's the exact same principle. Intersection functions the same way as and. Union functions the same way as or. Remember going back to our definitions. What did I mean by A? What does it mean for X to be in A union B? What does it mean for X to be in A union B? By definition, that meant X is in A or X is in B. That's what it means for X to be in A union B. And what does it mean for X to be in A intersect B? It means that X is in A and X is in B. What does it mean for X to be in A's complement? It means X is not in A. Or, if we write it out with explicit logic notation, it means not X in A. Make sense? So, using De Morgan's, let's just prove it out here really quick. I am going to show that the set A intersected with B, then take its complement, is equal to A complement union B complement. That's what I'm going to show. You with me? Okay, so the way we do that is we show they're subsets of each other. I'm going to show that if something's in here, it's also in here. And then if something's in here, it's also in here. And therefore, they're equal. You with me? So, well, I didn't need that. So we'll do X in A. Was I doing intersect first? Intersect. A intersect B complement. What does it mean for X to be in A intersect B complement? That's logically equivalent to it not being the case that X is in A intersect B. If X is in the complement of A intersect B, then it's not the case that X is in A intersect B. Which is the same thing as it is not the case that X is in A and X is in B. It's not the case that X is in both of them. Now we use De Morgan's. How do you distribute a not over the statement? You convert the ands to ors. So here's where we're using De Morgan's. this is the same thing as, it is not the case that x is in A, or it is not the case that x is in B. Right? And x not in A is the same thing as x in complement. So if it's not the case that x is in A, that's the same thing as x is in a complement. Right? And here's still our or if it's not the case that x is in B, that's the same thing as x is in B complement. And what does it mean for x to be in A complement or x to be in B complement? That's the same thing as x is in A complement union B complement. That's what it means to be in the union. It's in one or the other. So I just barely showed if x is in A intersect B complement, x is in A complement union B complement. And the whole heart of the proof is going from here to here. It's just De Morgan's. Make sense?
For your next proof, you would just go the other way, right?
Well, so I just barely proved if it's in here, then it's in here. But notice that these are all logically equivalent arrows. So if it's in here, then this is true, then this is true, then this is true, then this is true, then this is true. And so we just barely proved both ways. So we're done with this one. Everyone see how we're done with this one? Now, we don't need to write out the logic of this every single time. Hopefully, you can now see it. Here I have not A or B is equal to not A and not B. De Morgan's. Same thing. Writing it out here, it would look like this. A union B, that's logically equivalent to. So the complement of that is not x in that. Since it's a union, this is an or. When we do De Morgan's and we distribute, that turns that or to an and. So this was an and. So this was an intersection. There we go. We just proved the second one now. Same thing. Okay, that's De Morgan's. Now, I don't want to do a proof by induction to show that this works with any number. But it turns out it's the case that if I have A intersect B intersect C, and we look at their complement, this is still the same thing as A complement union B complement union C complement. So it's not some special thing that only works when we're talking about 2 sets at a time. You can apply it to 3 sets, or 4 sets, or 5 sets. This would be a simple proof by induction. You got your base case already done for you. But we won't do the proof by induction because I'm afraid some of you aren't comfortable with it, and I confuse you more than I help. So, but hopefully it appeals to your intuition that we can do this for any number. So that's what I'm saying here. If we're intersecting from I equals 1 to n, if we're intersecting together n sets, and then taking the complement, that's the same thing as unioning together the complement of those n sets. So if I take the complement on the inside, it just turns all my intersections to unions. Or if I had a union and I bring the complement in, it turns all my unions to intersections. So bringing the complement in flips your unions to intersections or your intersections to unions. In the same way that knotting flips your ands to ors and your ors to ands. It's the same logic. It's just a set version of it. Is that clear? The notation more scary than what I'm saying? As usual. Is this notation scary? Kind of, a little. Let's write a concrete case just to help it not be so scary. So when I do the intersection from I equals 1 to some number, I'm going to do 4 because I don't want to write too much, 4 of a sub I, then that's shorthand for A1 intersected with A2 intersected with A3 intersected with A4. And so if there's an n up here, that means keep going intersecting dot, dot, dot until we get to the nth one, whatever n is. So that's all that means. And similarly, when you flip it with union, it's just a bunch of unions of that. And so when I had it parentheses like that with a C out here, then that means take the complement of the whole thing. On the other hand, when I put the C inside of here, like that, then that means the complement applied to each individual set. No. For it to be the same thing, I'd have to split all my intersections to unions. When you distribute a knot over an and, it turns it to ors. When you distribute a knot over an or, it turns it to ands, De Morgans. If you remember that, you'll be good. Okay, so there was our huge detour with logic. Theorem. Let X tau be a topological space, then these three things are close. Okay, so I told you that closed sets and open sets almost have the same properties. They're so close it hurts. So, always and forever, the empty set and the entire set X are closed. Number two is that any finite number of closed sets, the union of any finite number of closed sets is still closed. Remember, up here it was the finite union of open sets is still open. The finite intersection of open sets is open. Over here, it's the finite union of closed sets is closed. And the logic there is, remember that these are just the complements of these. And so if you took the complement on this, that flips your intersection to union. And then down here, it's going to flip your union to intersection. So with closed sets, any arbitrary collection of closed sets, take its intersection, still closed. So it's just reversing. You can see how it's just taking the complement on these. That's all it's doing. Now we'll actually prove it, and all I'm going to do is take the complement of those. But hopefully, you want something to feel almost obvious before you try and prove it. So hopefully it feels almost obvious right now with everything we went over with De Morgans. So now I'm going to prove this. I'm going to prove that closed sets in fact have this property. So proof 1. So let X tau be topology. Which topology is it? We don't know. It's just some topology. We're going to show this as a case for any topology. Doesn't matter what topology it is. Or it's a topology tau. Guess you could say that. Yes. Which topology is it? It's tau. It's that one. Okay. Observe that X complement, what's the complement of X? It's the empty set. X complement equals the empty set is in tau, which gives me that X is closed. I showed its complement is in tau, so its complement is open. That's how you show a set's closed. How do I show a set's closed? I show its complement is open. What does it mean to be open? You're in the topology. So I showed X's complement is in the topology. So X is closed. 3. Observe that, what's the empty set's complement? X, which is in the topology. And so I know what? I know X is open, so I know the empty set is closed. Good. Okay. Got the hard part out of the way. Now let's prove the easy properties. Okay. So now I need to show that if you have n closed sets, I need to show that their union is still closed. Right? So next, let A1, comma, A2, comma, A3, dot, 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 AN be closed. Right? I don't know how. I'm trying to figure out if I want to name this thing. and let, what should I call it? V? V equal the union from I equals 1 to n of each of those sets. So I'm just going to let V be the union of all those things. So I don't have to keep writing this over and over again. All right, what am I trying to show?
V is closed.
I'm trying to show V is closed. So we have finitely many closed sets here. V is their union. I'm trying to show V is closed. How do I show V is closed? Show its complement is open. So 5. Then V complement is equal to V, the union from I equals 1 to n of a sub I, V complement. To bring the complement inside, all I have to do is flip my union to an intersection. So this is equal to the intersection from I equals 1 to n of AC. Now, A sub I complement. Okay. Each of these A's are closed. All the A's are closed. So all the A complements are open. So this is an intersection of finitely many open sets. And the intersection of finitely many open sets is open. The intersection of finitely many open sets is open. So that is in tau. So I just really showed V complement is in tau, which gives me that V is closed because its complement is open. Checks out? Double check the math? Okay. Usually is. The math always does, but do I? I wish my students did more. Okay, now let's do the next one. It's almost the exact same thing. 6. Let A sub alpha be any closed sets, or just let it be closed. We'll just say that these are closed. So now we have some arbitrary collection of them. Maybe infinitely many, maybe finitely many, maybe just one, maybe nothing's in there. But everything that's in there is for sure closed. So we have some arbitrary collection of closed things. And we'll let V equal the intersection of all those things. Right? What am I trying to show? I'm trying to show V is closed. So I'm trying to show V's complement is in tau. Perfect. So 7. Then V complement, which is equal to the intersection of all of these things, complement, is equal to, if I bring the complement inside, I flip the intersection to a union. So that's equal to the union of the complement of all those sets, which all of these A's are closed, so all their complements are open. So this is a union of open sets. And a union of open sets is always and forever open. So that is in tau. So that gives me that V is closed. Da, 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 da. We did it. So we just barely showed that closed sets always have these 3 properties. For any topological space, these 2 sets are closed. The union of finitely many closed sets is closed, and the intersection of any arbitrary collection of closed sets is also closed. Almost the same property as open sets. So real easy to remember them. you remember the properties for one, you instantly have the other. You just take the complement on each of these. Take the complement there, you get back those two sets. Take the complement there, that just flips that. Take the complement there, that just flips that. Okay, so we did that proof. Next, definition. So if X tau is a topological space, then we say it is Hausdorff,
German guy.
probably, good chance. It's Hausdorff, if and only if, for any 2 points in the topology you choose, for any 2 points in X you choose, that are distinct points, you can't pick the same point twice. Then there exist two neighborhoods. What's a neighborhood? It's just an open set containing that point. A neighborhood of X is an open set that contains X. And it's going to be easier for you to remember this Hausdorff property if you think in terms of neighborhoods. And I'll make that quick. Everyone who takes topology remembers what a Hausdorff topology is. And I'll give you the little mnemonic device we use to remember it. But first, let's get the property. So the topology is Hausdorff. This is a property topologies have. This is the first time we're talking about a topology now having a property. Up till now, we've just been getting used to terminology about topologies. So this is the first property we're saying. This is the type of property a topology has. Some topologies have this property, some topologies don't. And so this is a way that you can actually start classifying topologies. The topologies that are Hausdorff and the topologies that aren't Hausdorff. So this is our first topological property. Okay, so this topology is Hausdorff, if and only if. For any 2 points you choose, can't choose the same point twice. So they have to be two different points. X and Y can't be the same point. Then there exists two neighborhoods, two open sets containing those points, such that those neighborhoods do not intersect.
So they don't touch.
They don't touch. So if this is the standard topology on R2 is obviously Hausdorff. Pick any 2 points in X and Y 2 points X, Y you want. Here's 2 points. I can always find open sets containing those points that don't intersect. It's not saying every open set containing those points doesn't intersect. It's saying you can find at least 2. So I can do the open ball centered around this one and open ball centered around this one. Oh, there they are. And you say, okay, well, I chose my points even closer together. Doesn't matter. There's still plenty of room for me to construct 2 little small open balls that don't overlap. Okay, let me zoom in. And here they are. Right? Go ahead.
Why is it important to know if the topology is Hausdorff or not? Like, what does it give us?
Gives us as Hausdorff. So, this Hausdorff property, so this Hausdorff guy, he was one of the people initially coming up with what a topology has to have. Now, we broke it down to these 3 properties. This used to be a 4th property. He thought topologies have to have this property. So he had 1, 2, 3, and then he had this as an extra property on there. He thought topologies have to have this property. And then as more work was done in the field, we found out, well, there's actually these other things that are showing the things we expect topologies to have, and we want to include them in our definition of topology as well. So then there was a split, and they said, okay, so we'll call the ones that have this property Hausdorff topologies, and then we'll use the word topology more broadly. Okay? So topology means it just has these 3 properties, and the ones that happen to have this Hausdorff property, we'll call Hausdorff topologies. And Hausdorff topologies, they're really nice topologies. Most topologies we work with are Hausdorff. And it basically means any 2 distinct points you find, they're always separate from each other in some sense. 2 points are in some sense always separated from each other. Any 2 points you pick. Okay? That's what Hausdorff is essentially catching.
Why is that useful? Why is that important?
So we will prove that things that are Hausdorff have certain topologies or have certain properties. There's certain things we know if we know a topology is Hausdorff. And it turns out that a lot of the topologies that we are interested in, like the standard topology on R, A lot of these topologies are Hausdorff. And so we know right off the bat, okay, then they have all the properties that we already proved Hausdorff topologies have. So instantly gives us some information into a bunch of topologies that we're often interested in. Topology classification is one of the major fields of research in topology right now. Classifying topologies. Saying it has this property, doesn't have this, has this, doesn't have this. And so here's something that's actually distinct between topologies. Some topologies have this property, some don't. So this is a way that we can actually say, no, these two things are in fact different. Because sometimes it gets really hard to say whether one topology is different from another. Because remember, in topology, a circle is in some sense equivalent to this thing. And so we are very interested in these properties on how we can actually say that they're different in topology when we preserve such little structure. So, a lot of reasons. Just another property, another interesting property that turns out to be useful. But this one's got some nice history to it because it used to be one of the things that we had over here.
What is an example of non-Hausdorff topology?
The finite complement topology is not Hausdorff. And we'll prove it. Okay, so first off, Hausdorff. Let's get intuition for it. The way we think about a Hausdorff topology is that for any 2 points, you can house them off from each other. They can have their own neighborhoods. These guys do not have to hang out. You can house them off from each other. The Hausdorff topology. They get their own neighborhoods. Any 2 points have their own neighborhoods. Hausdorff. So that's how you remember. What's a Hausdorff topology? Oh, that's when you house off the points from each other. Any 2 points get their own neighborhood. So that's essentially what Hausdorff is saying. Go ahead.
So does that mean that for your second example on the second thing that topology is not Hausdorff because there is no A separate?
You're saying this one?
Yeah, from B.
This one is definitely not Hausdorff. Correct. Here's C and D. They don't have their own neighborhoods. So if you have a finite topology, the only way for it to be Hausdorff is if it's a discrete topology. Okay. Next. Okay. This. So if a topology is Hausdorff, then any singleton set has to be closed.
Makes sense.
And let's prove it. I don't know how much room I'll need. Maybe I don't have to. Well, we're going to have to create some of those. Just erase it. Okay. So proof. Proving this. So 1. Let x tau be Hausdorff. Comma, and let little x be any point in big X. What am I trying to prove? I'm trying to prove that the set containing little x by itself, just that set, is closed. That's what we're saying. If a topology is Hausdorff, then for all little x and big X, the set containing just that little x is closed. So I need to prove that that set is closed. So 2. Let V equal that set's complement. So I'm trying to maybe call it U, since we're going to prove it's open. Maybe I don't want to say it again. Not sure how I'm going to do this, but I need to use the fact that the topology is Hausdorff. What does it mean for it to be Hausdorff? It means it has this property. So let me just get another point in here. That's not x. So 2. Let y be some other point in x such that x is not equal to y. Okay, I think I have an idea on how to do this. Sorry. Don't do that, don't do that. So let x equal that, comma, finally, and let u equal the complement of x. Okay, so I'm trying to show u is open. So drawing a picture, the set containing x is just that. So u over here is everything except this point. Here's what I'm going to do. I'm going to show that for any point y in u you choose, pick any point y in u you want, I can find an open set containing y such that, we'll call it v sub y, or no, I'll call it u sub y. For every point y in u, I can find an open set u sub y containing y, where u sub y is a subset of u. And so then u is just going to be equal to the union for every y in u of all those u sub y's. Same idea that we already used in this class. We use this idea over and over again. You remember all the way back, those of you who are here for the preliminaries? This is called the union lemma that we keep using over and over again. Union lemma, union lemma, union lemma. So by the union lemma, u is equal to the union of all the open sets containing all the points. That's big picture how we're going to do this. So, 2, let y be any point in u. And observe that x is not equal to y. How do I know that y isn't x? Right. X is the one point missing from u. I can't pick something out of u and have it be x. It has to be something different from x. So I'm guaranteed that this point in u is something different from x. What does that mean? Well, since it's Hausdorff, that means that there exist two neighborhoods that don't intersect. So that gives me then that there exists v sub y comma u sub y such that x is in v sub y is in u sub y, and v sub y intersect u sub y is equal to the empty set. So I know since it's Hausdorff, you pick y, then there must exist some open set containing y, we're calling it u sub y, and some open set containing x, we're calling that one v sub y, such that these two open sets don't intersect. Right? And since those two open sets don't intersect, I'm guaranteed that the open set containing y, I'm guaranteed that this u sub y doesn't have x. It doesn't have x because x is in v sub y. So that gives me that x is not in u sub y. Because x was in v sub y. X was in that one, can't be in that one. It's Hausdorff. Which gives me that u sub y is a subset of u. U is everything that's not x. U sub y doesn't have x, so it must be in u. Okay. So we just barely found, bring all the pieces home, we just barely showed that y is in u sub y is a subset of u. I just barely showed how for any y, I can find an open set containing y, where that open set is a subset of u. Then by the union lemma, 3, by the union lemma, u is equal to the union for every little y in u of all those u sub y's. And since u is a union of open sets, that gives me u is open. It's a union of open sets. Oh, if u's open, then its complement is closed. Excuse me, that is closed. Sorry. Hope you followed all the logic there.
A little bit. In the end there, wouldn't that imply that b sub y is closed, so the complement is closed, so b is closed. And then wouldn't that imply that your second containing x is closed?
V sub y, we just use V sub y for a second. The only reason we have V sub y here is to make sure that we just need to say, look, there's a u sub y containing y that doesn't have x.
I understand that. I'm talking about the end of your proof in your last implication.
So there's no more V sub y's after that.
Sorry, not b sub y, but b itself, the complement of u.
The complement of u is just a set containing x.
Oh, I see.
U is equal to the complement of x.
Yeah.
And we just barely showed u is equal to a union of open sets. So u is open. U, by definition, is a complement of x. So that means the set containing x is closed, because the complement is open.
Okay, I follow that.
Good? Nice, nice. All right. We did that. Let's look at this one. The standard topology on R is Hausdorff. R sub st is Hausdorff. We're going to prove it. I'm going to show for any 2 points you pick on the real number line, we can find open sets containing them that are disjoint. Yeah, this is stupid easy. All right. You're saying obviously. So prove that the standard topology on R is Hausdorff. I think there's 2 F's, yeah. 1. Let x and y be any 2 points in R such that x is not equal to y. Draw a picture over here. Here's x, here's y. 2 points that aren't the same point. What's our job? Our job is to show that we can find an open set containing x and an open set containing y such that those 2 open sets don't intersect. That's all we need to do. So in other words, I just need to find 2 open intervals, one containing x and one containing y, where those 2 open intervals don't intersect.
Is this similar to how you did your triangle thing with 3 different points?
This one's even easier than that.
Take the difference between them, cut it in half, and make those halves small.
You just take half the distance between them and extend it out that far.
Okay.
So let this one go. So we can just find the middle point here, M, and we can just include -1. Well, we don't know where it starts, so shoot. We're actually going to have to calculate distance here. Oh, no, we can go back 1. Okay, let me say one more thing. Back 1 or forward 1, I need to know which one of these numbers are bigger or smaller. Just so I know which one's ahead and which one's behind.
Backwards 1 and forwards 1.
No. I'll show you what I mean. So let x and y in R such that x is not equal to y, comma. And here's another one we do all the time. Assume without loss of generality that x is less than y. Pretty common one. You just see the log. The log. Yeah, it's a common one that comes up a lot. So assume x is less than y. What if x was actually greater than y? Relabel them. Call the smaller one x and the larger one y. Doesn't matter. So without loss of generality, we can always call the smaller one x. Okay. 2. Let m equal x plus y over 2. What is m? The midpoint of the two. It's their average, their middle point. That gives us that x is in the open interval from x minus 1 to m. Y is in the open interval from m to y plus 1. And the intersection of these two things is equal to the empty set.
Are you using one for a reason, or is it irrelevant?
It's irrelevant. This could have just as easily been 99. And this one over here, 32. It's just some open interval. So what do we have? Looking at this, here's x, here's y, and then m I calculate to be their midpoint. So m's right here. So the interval around x goes to m. Here's its ending point. And where does it start? It starts back 99 from x, wherever that is. There's an open interval containing x.
I see.
That's why we need to know which one was ahead out of x and y, so I knew whether m is the start or the end point. Y starts at m, but doesn't include it, so no overlap there. And it goes all the way to y plus 32, up there somewhere. And it's that open interval. So there's an open interval containing x, there's an open interval containing y. They don't overlap.
So why not just substitute for variable? Why are you saying a specific number then?
Because we just need to show so a topology is Hausdorff. If for any 2 points you choose, I can find some neighborhood containing those 2 points. I can find some neighborhood for the first point and some neighborhood for the second point, such that the two neighborhoods don't intersect.
Well, this isn't like a for all.
No, this is just there exists some that does
So
it.
you can say that
I see.
it is x plus, well, x minus s and y plus s, where s is any number of real numbers.
That would have worked. But we still picked a very particular starting number, m. So, yeah. Would have been fine, would have been fine. What we did is fine. We just need to find one. We found it. Okay. Lower limit topology. The lower limit topology, so the standard topology on R is using open intervals A, B. The lower limit topology on R is using intervals like this, A, B, like that. That's the lower limit topology.
Wouldn't you just use,
We could do the exact same method we just used.
how would you do that with a closed one though?
Well, look. We're just showing it's Hausdorff.
Yeah, but Hausdorff involves open sets, right?
No.
Or
Oh, now open sets look like this. So now, if we were doing this for the lower limit topology, then let x, y be any 2 points, and assume without loss of generality, blah, 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 let m be the midpoint. Then x is in here, and y is in here. This one goes up to m but doesn't include it. This one starts at m and continues onwards.
oh, so they're still not touching.
So they're still not overlapping. So they're still Hausdorff.
I see.
Now, this one is a funny topology because all these things, A, B, in the lower limit topology, are both open and closed. Because what's the complement of that? It's all the numbers from negative infinity to A, which we could create with a bunch of these, union together with starting at B and going to infinity. So the complement of that is that. This is open in the lower limit topology, so that's closed in the lower limit topology. So that's both closed and open. Well, we don't work much with the lower limit topology, so not as worried about you getting intuition for that one.
Wouldn't that also imply the opposite of that? So
If it's
not including A, but including B?
Yeah, the same thing would be true of the upper limit topology.
Okay.
Yes. Okay. And then finally, lastly, we're going to prove that the finite complement topology is not Hausdorff. We're going to prove that it's not Hausdorff. Proof. Well, we won't bother writing it. So 1, let tau be the finite complement topology on X, comma, and assume, by way of contradiction, that tau is Hausdorff. Two F's, thank you. Here, we're running out of space here. Let's come back and rewrite up here as we need. All right, put one more line on here. 2. Let X and Y be any 2 points in big X such that X is not equal to Y. And what does that give me? That gives me that there exists U sub X and U sub Y in tau, where X is in U sub X, Y is in U sub Y. That's usually what's understood from the syntax. I'm going to stop explicitly saying that. U sub X and U sub Y in tau, such that their intersection, U sub X intersect U sub Y, is equal to the empty set. You with me?
Yeah.
3. Then U sub X intersect U sub Y complement has to be equal to
Full set.
the empty set complement. Good. Which gives me U sub X complement union U sub Y's complement has to equal the whole set, R. Now here's my contradiction. Let's see how that's a contradiction. What topology are we in? The finite complement topology. What's the finite complement topology? What are open sets in the finite complement topology? They're all the sets whose complement is finite. So you're only open if your complement is finite. So if U sub X is open, then U sub X's complement must be finite. And U sub Y's complement must be finite. And the union of finite sets gives you a finite set.
I see it.
And R is not finite. That is very non-finite or infinite. All right. So therefore, it's not Hausdorff. Proof by contradiction. Good? Okay. So that finishes chapter 1. Next week, we'll start on chapter 2, talking about interior enclosure. It's going to be a good time. Working our way up to limits. We're so close. Sorry, any questions before I turn this off?